Welcome. Before we dive into the depths of low-level design, it's essential to revisit the core principles that shape modern software development, the four pillars of object-oriented design. These pillars, encapsulation, inheritance, polymorphism, and abstraction, are the foundation for building robust, maintainable, and scalable systems. In this video, we'll break down each concept with relatable examples, so whether you're refreshing your knowledge or learning for the first time, you'll walk away with a clear understanding. Let's start our journey by exploring what makes these principles so powerful in the world of programming. Object-oriented design isn't just a buzzword. It's a proven approach that makes software easier to understand, maintain, and extend. By organizing code around real-world objects and their interactions, developers can manage complexity and adapt to changing requirements more effectively. These four pillars serve as guiding principles, ensuring that your codebase remains clean and flexible as it grows. Now, let's begin with the first pillar, encapsulation. Encapsulation is all about protecting an object's internal state by controlling how its data is accessed and modified. Think of it as a protective barrier. Only specific methods can change or retrieve the data, preventing accidental or unauthorized changes. For example, a bank account class doesn't let anyone directly alter its balance. Instead, it provides methods like deposit and withdraw, ensuring that all business rules are consistently followed. This not only prevents invalid states, but also makes your code more reliable and secure. Imagine you have a bank account object. Instead of letting anyone set the balance directly, you provide deposit and withdraw methods. This way, every change to the balance goes through a controlled process, applying all necessary checks and rules. If someone tries to withdraw more than the available balance, the method can prevent it. This approach keeps the account in a valid state and ensures the logic is consistent throughout your application. Encapsulation brings several advantages to your code. It makes your objects safer by hiding their internal details and exposing only what's necessary. This reduces the risk of bugs caused by unintended changes. It also makes your code easier to maintain, since you can update the internal implementation without affecting other parts of your program. Overall, encapsulation leads to more robust and reliable software. Now let's move on to inheritance. Inheritance allows one class to reuse the properties and behaviors of another class. This means you can create a general class with common features, and then build more specific classes that inherit from it. For example, both car and bike can inherit from a vehicle class, sharing common functionality like start or stop. This approach reduces code duplication and makes it easier to manage shared logic. Consider a vehicle class that defines basic behaviors like starting and stopping. Both car and bike classes can inherit from vehicle, automatically gaining these features. If you need to add a new type of vehicle, you simply create a new class that inherits from vehicle. This keeps your code organized and makes it easy to add new functionality without rewriting existing code. Inheritance promotes code reuse and consistency. By defining shared behavior in a base class, you ensure that all derived classes follow the same rules. This not only saves time but also makes your code easier to understand and maintain. If you need to update a common feature, you can do it in one place, and all related classes will benefit from the change. Third pillar, polymorphism, means that the same operation can behave differently depending on the object. This is especially useful when you want to write flexible and extensible code. For example, in a payment system, you might have different payment methods like credit card, UPI, or digital wallet. The application simply calls payment service pay, and the correct implementation is chosen automatically. This makes it easy to add new payment methods without changing existing code. Imagine a payment system where you can pay using different methods. Whether it's a credit card, UPI, or digital wallet, the application just calls the pay method. Each payment type has its own implementation, but the interface remains the same. This design allows you to add new payment options in the future without touching the existing code, making your system more adaptable and future-proof. Polymorphism makes your code more flexible and easier to extend. By allowing the same operation to have different implementations, you can introduce new features with minimal changes. This reduces the risk of breaking existing functionality and helps your software evolve smoothly as requirements change. It's a key reason why object-oriented systems are so powerful. Final pillar is abstraction. Abstraction means hiding unnecessary details and exposing only what users need to interact with. Think about driving a car. You use the steering wheel, accelerator, and brakes, but you don't need to know how the engine works. In software, abstraction provides simple interfaces while hiding complex implementation details, making systems easier to use and understand. When you drive a car, you interact with the steering wheel, pedals, and gear shift. You don't need to understand the mechanics under the hood. Similarly, in software, users interact with simple interfaces, while the complex logic stays hidden. This separation makes it easier for users and developers alike, as they can focus on what matters most without being overwhelmed by details. Abstraction helps manage complexity by exposing only the necessary parts of a system. It allows developers to work with high-level concepts without worrying about the underlying details. This not only makes software easier to use, but also simplifies maintenance and future enhancements. By focusing on what's important, abstraction keeps your code clean and user-friendly. To wrap up, let's quickly recap the 4 pillars of object-oriented design. Encapsulation protects an object's state and controls how data changes. Inheritance enables code reuse and consistency. Polymorphism allows the same operation to have different implementations, making systems flexible and extensible. Abstraction hides complexity and exposes only what is necessary. Together, these principles form the backbone of effective software design, helping you build systems that are robust, maintainable, and easy to extend.